Hey, good afternoon, my friends. Brandon Steckler, technical editor of Motor Age Magazine, and I want to welcome you back to another episode number 28 of Mastering Diagnostics. And today's episode is about demonstrating the effects of Ohm's Law. And we are going to be leveraging several snap-on diagnostic tools to do so. Now, what I'm getting at is my diagnostic approach from years ago now is based around physics, the physics that drive our automotive systems. And the reason why I base my diagnostic approach around these physics is physics cannot be changed. They are theories that have been proven time and time again, and we can rely on them. This is something that we can lean on, we can count on over time as we carry our way through tests, and leads us to anticipation on what these test results should be if the components within the systems residing on the circuits are in fact functioning as designed. So to ignore those laws of physics, to hide from them, would be a mistake. And I know many technicians, probably most of us, if not all of us, or neither of us, I should say, signed up to be scientists when we agreed to be working on vehicles. But that is in fact what we are. We leverage tools. We develop theories based upon the knowledge we've acquired over years. We leverage tools to test those theories, and through our hypotheses, then determine, is the system doing what we expect to do or not? And then we have to make repairs or suggestions on how to correct those faults accordingly. So learning to embrace these physics, these electrical laws, if you will allow us to leverage our tools to demonstrate the physics that are at play. And we do that, we can evaluate the systems, but more importantly, the components that reside in those systems on circuits. Individual components, learning how they work and these laws of physics will allow us to determine if they're functioning properly or not, and more importantly, where the fault lies. So in order to do that, we have to have the right tools for the job. And the right tool for the job will allow you to truly evaluate those components in those systems on those circuits to determine if they're functioning right or not. And being able to leverage physics as well as the appropriate tooling and the right technique with your technical know-how will allow you to be far more accurate than taking guesses or performing tests that don't revolve around physics, like moving parts around and such. Having that accuracy, and with a little bit of practice, you develop some efficiency. And when you have accuracy and efficiency, you get confidence. And that is where the true success comes into play. That's where we really start becoming efficient, and even in a flat rate world, begin to make money. Contrary to popular belief, my success as a diagnostician, even financial success, has nothing to do with me running at a fast pace, running around like a chicken without a head. Believe me, I'm no faster than anybody else as far as being fast on my feet. But I do have a process that I always aim to perfect over time. I always want to be better than I was the time before. And following through with that wildly important goal of being better than I was the day before allows me to maintain or improve my efficiency. And this is where my confidence comes from. So again, I want to offer special thanks to Snap-on Diagnostics. Right here over my left shoulder is the Snap-on Zeus Plus. And using the Snap-on Zeus Plus DVOM voltmeter as well as the 4Trace lab scope, I am going to prove out the functionality of some components that are not really working properly on my vehicle. I'm also going to be backing up my theory with the Snap-on Diagnostic Thermal Imager. The point is, my 2006 Chevy Silverado is experiencing an issue with the blower motor. The blower motor seems to function just fine in switch positions 2, 3, 4, and 5. However, it doesn't seem to function at all in position 1. Now, I have a theory on what might be going on due to my experience with vehicles like this and the system and the way it's comprised. But of course, I always want to test my theory. I don't want to guess. I want to be accurate. So what we're going to try and prove out today is Ohm's law. More importantly, the effect of Ohm's law. And we have to first begin by understanding what Ohm's law is. And when I say that, I don't mean the written down paragraph version of Ohm's law, something you read in a book and attempt to memorize. That didn't help me fix cars. By truly understanding what Ohm's law means, the relationship between resistance, current flow, and voltage being electrical pressure, current flow being the movement of electrons through a circuit, much like water through a pipe, and resistance, the opposition to that current flow. All three of those angles, they relate to one another and allow us to develop anticipation on what we should be measuring, depending on how the circuit and the components within that circuit are behaving. And there is another point I want to bring about. Current flow is the work truly being performed in a circuit. So, for instance, if we were monitoring an electric stove or a rear defroster grid, as those circuits begin to function and current flows through those circuits, the resistance within those circuits creates voltage drop, pressure drop, electrical pressure drop. And the results of that pressure drop amounts to heat. And heat given off in the form of light or actual heat that we can feel that melts ice in the case of a rear defroster grid or boils water on a stove. That heat is the result of that voltage drop. And many times when we have issues with circuits, especially like this blower motor, we have excessive voltage drop and or excessive current flow. We get excessive heat and it causes things to break down thermally. So leveraging the power of our Snap-on Zeus multi-trace lab scope, as well as our EETA 308D low amp probe, we're going to prove the circuit's functionality or malfunction, and we are going to back up our theories with a thermal image from our Snap-on Diagnostic thermal imager. So with the tools, Snap-on also passed over another gift to me, access to Snap-on's Shop Key Service Information System. Shop Key Service Information Systems allows me to quickly not only research the wiring diagram, but allows me access to component location, as well as the pinout of the connectors, being able to identify specific surface so I can triangulate where it is I want to place my test leads and carry out the tests in the fashion I desire. And I do that right here at my desk where I can do my best thinking. It's only then when I've developed that game plan through valuable service information systems like Shop Key, I can then head out to the vehicle and carry out the test I devised here at my desk. See, when we head out to the vehicle, we are simply asking questions of the vehicle and waiting for answers. And the answers in the form of test results should answer our question about where to test next or which components require attention. So heading over to the wiring diagram, I've zoomed in on this here to make it a bit more visible for you. We can correlate the colors of these switch contacts to the circuitry related to the blower motor itself. And what we have here is a series of 4 resistors of different values. So in switch position number 1, what we call the red switch position, the yellow wire allows voltage to make its way all the way to terminal A of our blower motor resistor assembly. And because the blower motor relay is relaxed, it's not energized, the switch contact falls in this position, allowing current to flow through the blower motor that is always grounded at G200. So as a result, voltage will be applied, and as electrical laws of physics designate, all the voltage in a series circuit must be dropped by the time we get to ground. So what I'm getting at here is with 12 volts applied to this red terminal, the 12 volts will be dropped across these proportionally to the amount of resistance value each one of these possesses. So we start with 12, there'll be a little bit less here, less yet here, even more or less here. And by the time we get to the blower motor, instead of having 12 volts pushing this motor, we will have significantly less, probably closer to 4 or 3. Who really knows, not till we get out to the vehicle. So now that we have an idea of what it is we have to do and how the system is configured, we can develop our test plan. Using that wiring diagram, we're going to be placing our leads accordingly. We're going to be sampling available voltage at the blower motor and available ground at the blower motor and check it in the operative positions of that switch. And then we are going to check it in position number 1 where the blower motor is not functioning. And depending on our results is where we perform our next test. Is the problem somehow at the blower motor resistor, or are we having an issue all the way up to the switch? These are things we will only find out once we perform our tests. So let us head out to the vehicle now and carry out these tests. So we're in the truck now. And again, the simple problem is that the blower motor works on all speeds, including high, except for speed number 1. I put it on speed number 1, nothing's going to happen. So again, the idea isn't what's wrong, how do we diagnose the problem? The real question is why, right? Why did this failure occur? So of course, we're going to begin at the beginning and find out why the blower motor isn't working on speed number 1. And that's going to be a simple diagnosis we're going to demonstrate in a minute. But then we're going to follow through to determine why. So I've got my Snap-on Zeus set up and on the circuit that we're going to be measuring. And first we're going to reference the wiring diagram. I'm going to show you what it is I was looking at to determine where I'm going to place my test leads to figure out quite easily what's going on. Here's our blower circuit as we described earlier on the computer. And we're going to be over here in position number 1. Position number 1 is going to allow voltage to travel through the yellow wire over to our resistor. Now, when I turn it on in this position, the blower does not work. We have to first determine, do we have voltage there? What are some of the questions we can answer? Is the blower functional? Of course it is. It works in every other speed. So it's clear that we have a good path to ground, and it's clear that we have a good motor with no opens from here down, and with all the other switch positions allowing the blower motor to function. The likely culprit is an open resistor here. But before we jump the gun, let's do a quick simple test. So again, I've got my Snap-on Zeus Plus set up ready to rock and roll. Here's the circuit we are looking at. I've got my red Pierce probe here attached to the red wire connecting straight to the blower motor at the voltage feed side. This black Pierce probe is connected to the system ground. So let's reference the diagram once again. My red lead is connected right here, and my ground lead is connected right here. So I'm simply going to be manipulating the switch in different positions. But you'll see when I get to position number 1, listen, it goes away. So let's set up our Snap-on Zeus Plus, leveraging our multimeter. To allow us to see what we need to make diagnostic decisions about what's going on. So the system is off. My scope module is connected to my Snap-on Zeus Plus, and my wire leads are connected to the appropriate circuit and the scope module. So let's watch what happens in position 5. Nearly source voltage. Of course, the engine isn't running now, so that's why it appears to be low voltage. There's position 4. It's only natural to assume voltage will be less because current flow follows voltage, and if voltage is lower, less current will flow and less work will be performed, hence the slower speed. Let's go to position 3. Lower voltage yet. Position 2. And of course, position number 1, which yields us no voltage. So as always, we got to ask why. Why is there no voltage output to the blower motor in position number 1? Well, that means we got to step back. We're going to be placing our test lead right here. I'm going to leave my black lead here because it references ground. We know it's a good ground. And we're going to be testing right here. It's obvious all these other ones have integrity because we get voltage down at the blower motor when we were in switch position 5, 4, 3, and 2, but not in position 1. So what we're going to do now is move our test lead from the blower motor positive, which was the red wire, up to terminal B of the resistor module, because terminal B is at the resistor module where it should be received voltage from switch position number 1. So we're going to remove our test lead from here, and it reads A, B, C, D, E, F, G from right to left. So this would be terminal B right here. We're going to connect our pierce probe. I always pierce wires. Well, I shouldn't say always. I almost always pierce wires, just to ensure I have good connection to the circuit. We can always repair them later. So, let's hit the switch and see what happens. Of course, the blower's not functioning, but we do have voltage supply proving that our switch is functioning. So for a moment, let's talk about the results of our test and what it tells us as diagnosticians. 12 volts available right here means the switch closed appropriately and allowed voltage to travel down the yellow wire, but it stops here. With voltage present here, and here, and here, and here, and here in their respective switched positions, with the blower motor functional, it infers that this entire resistor module, if you will, is intact. However, the integrity of this resistor module has broken down right here. So this resistor is no good, and by replacing this resistor assembly, we're going to fix the problem. So if we put the blower motor resistor in, what's going to happen? The circuit's going to work just fine, and the blower motor is going to function as it should in all switch positions. But the question is, how long until this vehicle comes back with a similar or the same exact failure? That's the question many technicians fail to answer because they don't dig deep enough. You see, there's always a reason why. And I found in my experience of mess-ups and comebacks that if we continue to pursue the question why, ask why 5 times, more often than not, you get to the root cause of the problem. In other words, why is the customer here? The blower motor doesn't work in position number 1. Why doesn't the blower motor work in position number 1? Because the resistor's open. The question should be next, the third question of why is the resistor open? Now, if you think about it, going back to Ohm's law, we were discussing how heat is a byproduct of voltage drop. And voltage drop increases with an increase in current flow. So over time, as a DC motor, for instance, begins to bind or wear, or perhaps has taken on some water ingress, and the motor can tend to draw more current. So again, going back to Ohm's law, if the motor draws more current, we're going to have more voltage drop, and with more voltage drop comes more heat, and this is what causes these resistors to melt down. So here's what we're not going to do. We're not going to take my word for it. We're going to be thorough diagnosticians, and we are going to perform tests that will conclusively prove the blower motor is drawing more current than it should be drawing. Not enough to blow a fuse. The fuse is rated at 30 amps. So as long as the circuit stays below 30 amps, we're not going to blow the fuse. But if that blower motor was supposed to be drawing about 15 amps and is now drawing 25 or 26 amps, just for instance, we're not going to blow the fuse, but we are going to overload the circuit. And in this case, the resistors creating the voltage drop are going to see a lot of heat, just like a filament in a light bulb or an electric stove element, or heck, even the rear defroster grid. So let's perform some testing that proves the work being performed by the blower motor. We're going to do that on this older motor, and we're also going to do it on our replacement motor. And I'll show you what it is I'm talking about, getting to the root cause simply by asking why. So now, to measure the work being performed, I'm going to be implementing the snap-on low current probe, the EETA 308D, and this is going to measure the current flow through the wire, and that is the work being performed in the circuit. It's very important you always measure the work being performed in the circuit because it's going to allow us to determine the root cause of the fault in this scenario. We are going to be measuring voltage at the motor, ground supply at the motor, and current flow through the circuit. Anywhere in a series circuit you can measure current. So it's going to be ideal to go right here because we're standing right here anyway. So we've got our amp probe connected in series with our blower motor. We have got the amp probe set up at a ratio of 10 millivolts output for every 1 amp sensed. So we're going to use that information to set up our scope. So if we go to our scope setup, our traces, we've got channel 1 set up to measure voltage at the blower motor. We've got channel 3 ground supply at the blower motor. Channel 4, again, set up for a 60 amp scale. Now we're going to exit and set up our time base. We're going to change our sweep. We put 20 seconds on the screen. Gives us plenty of information, and all that's going to be stored in our data buffer if we want to review it later. So I've got all the traces pulled down here, down low to 0. Everything's zeroed out. My probe is on and zeroed. We are going to run the blower motor on high and capture amperage, as well as voltage and ground supply to that blower motor. And we're going to repeat this process with a new blower motor in place. So this data is being captured now. So as we can see, we've got nearly in yellow, just about 14 volts available. Our ground potential staying really low, so that proves voltage and ground are good. And current, the work being performed, is resting at just about 20 amps on high. So what I want to do real quick is capitalize on some of the tools the Snap-on Zeus Plus will allow us to leverage to help make better diagnostic decisions, some measuring tools, if you will. What we're going to do is deploy cursors. So if I come up here to the cursors button and I hit show, I can move them wherever I desire. And cursor 1 and cursor 2 are both referencing the same location, of course, on the red current trace. That's our work being performed. And both are indicating, as they should, the same 20 amps. However, it also shows a maximum inrush current of 70 amps. So let's keep that in mind as we pursue this, especially when we put the new components in. We'll see the difference. So to prove my point even further, discussing Ohm's law, the relationship between voltage, electrical pressure, current flow, the movement of electrons through a circuit, and resistance, the opposition to that current flow. Again, as current flows, voltage drop increases, and with voltage drop, we have heat. I'm going to prove that point with the Snap-on Diagnostic Thermal Imager. We're going to leverage this tool to show the heat signature created by the blower motor. Now, to keep an apples-to-apples comparison, what I'm going to do is allow this blower motor to operate for exactly 5 minutes before I take the measurement. Allow it to heat up and all that heat to saturate the plastic and the surrounding material around the motor armature, just to give us a fair shake between the old motor and the new motor. Again, I'm going to start a stopwatch, and at 5 minutes exactly, I'm going to shut off the blower motor and measure the heat signature. And we're going to repeat this process with the new blower motor in place afterwards. So, it's been 5 minutes. I just turned off the blower motor. We've got our Snap-on Diagnostic Thermal Imager ready to rock and roll. And I'm going to grab an image. And I have it captured. We'll view it later and then compare it to the new one. So we've got the new blower motor and resistor assembly in. We've still got the scope set up, and we are going to capture current once again, and we're going to see the difference. So with the scope set up, we're going to once again deploy our cursors and go to high speed. I should do it. Let's pause the screen. And our amperage is about 18, 19, but more importantly, look at our inrush current. Our inrush current is down to about 60 amps. On the original motor, it was over 70 amps. So what we're going to do now is let the motor run for about 5 minutes, just like we did before. And we're going to measure temperature, both the connector and the motor armature at the base of the motor assembly itself, and see the difference. The evidence is pretty conclusive. On the left side of the screen, we are staring at both the raw image and the thermal image combined on the same screen of the Snap-on Diagnostic Thermal Imager. And this is the temperature. Once the machine has been calibrated, this is the temperature of the surface of the blower motor resistor itself. However, after we replace the blower motor and replace the resistor and repeat that same test, again with the 5 minute run time, we took the same exact measurement, and it is 13 degrees cooler, backing up the correlation between current flow, voltage drop, and heat. So as you can see, it's not rocket science, but it is science. and we take the opportunity to understand and leverage these electrical laws of physics to our advantage, we can then apply them using the appropriate tools. In this case, like the Snap-on Zeus Plus, the Snap-on EETA 308D low amp probe, and the Snap-on Diagnostic thermal imager. Together, we were able to tell the story about what was wrong with the blower motor, why it wasn't functioning properly, specifically in speed range 1, and the underlying cause of the failure so we don't have a repeat comeback, if you will. Being able to capture information at this level to answer the question why until you can't answer it anymore prevents comebacks and allows you to fix the vehicle appropriately, the right way, on the first visit. I'm Brandon Steckler, Technical Editor, Motor Age Magazine, and I thank you for joining me on this episode of Mastering Diagnostics. Take care.